So our first reaction mechanism here is one that's actually intentionally meant to be something that we get wrong, because remember, oftentimes when we get something incorrect, that's where we can learn from it. So truthfully, I'm more surprised if there's a lot of students who get this right versus kind of what I'm going to show you first here, which is an incorrect mechanism. So kind of building on some of the concepts that were discussed in the intro video, when you're asked to do a reaction mechanism, more often than not, you probably won't have a question mark at the end here. I will give you a specific product because there's way too many options for different side reactions, different side products that could be made, that I need to sort of direct you where you're going. But this problem isn't intentionally written this way because most students take this first approach. And to build on some of the skills that were introduced in the intro video here, when you're asked to do a mechanism, begin by drawing chemical structures of the reacting species, showing lone pair electrons and all atoms that are relevant for the chemistry. And so in this case, we have a carboxylic acid and an amine. Most students then do a very good job of identifying which species are nucleophilic and which species are electrophilic. So your amine is going to be your nucleophile. Your carboxylic acid is going to be your electrophile. But this is where students then kind of go off in an incorrect direction. So while the nucleophilic atom of our nucleophile is the lone pair of electrons on nitrogen, and more often than not, we're going to see a lot of carbonyl chemistry where the carbonyl is electrophilic. In this case, and we'll highlight this in the correct mechanism in a moment, the hydrogen atom is actually the best electrophile. But let's carry this mechanism through with what most students come up with. Nucleophilic attack on the electrophilic carbonyl, generating a tetrahedral intermediate. And I do want to highlight that this is a very common theme that we are going to see. Many of the reaction mechanisms that you have will have carbonyl containing compounds. Generation of a tetrahedral intermediate. Again, making sure that we balance all atoms and charges. Now, commonly what we'll see is students will write a PT for proton transfer because they recognize that we need to change who is the good leaving group here in order to generate an amide. So we need to deprotonate this protonated nitrogen over here, the protonated amine, because that is the best leaving group in this tetrahedral intermediate. And we need to protonate the hydroxyl group to make it into water, which is the leaving group that we'd want to have. So again, we still maintain the same overall charge balance, but we've changed who is the better leaving group here. Kind of collapse of that tetrahedral intermediate. So again, reformation of the carbonyl CO bond, double bond there with the elimination of, in this case, what's the best leaving group, which is water, is going to generate our amide. And then elimination of water. And truthfully, when we do see chemistries that generate amide functional groups, these are condensation reactions, and so we see the production and thus the elimination of a small molecule when we condense these together and we eliminate water. And that is typically what we are going to see when we generate amides. But as I've already kind of highlighted, this mechanism is not one that is going to effectively generate an amide, and that's because there's a better electrophile. We have our better electrophile here in our proton. Don't ever forget that protons can be good electrophiles too. So I just kind of want to highlight here a couple of things. Again, carbonyl containing compounds are going to be the bulk of reaction mechanisms that we'll deal with, and that's because a carbonyl containing functional group is a great electrophile. But we always have to remember that protons are really good electrophiles too. Wanted to highlight here that we do tend to see reversible reactions that we have here in most of our reaction mechanisms, so that this reaction could proceed in either way. And in this case, we should have shown this proton transfer to be a reversible reaction as well. But I do want to highlight that we're not going to show proton transfers simply as a PT. I do want you to use solvent to show the movement of protons such that we see the deprotonation here of our amine functional group to generate the neutral amine, and then the protonation of that hydroxyl group to make the better leaving group in water. And the reason that we're going to show those proton transfers is when we map a lot of these reaction mechanisms onto chemistry that we see in enzyme active sites, those protonation and deprotonation events are generally what the amino acids in the catalytic active site are doing. They're often doing protonation and deprotonation steps, and so we want to make sure that we see how those map onto a reaction mechanism so we can better understand how amino acids are going to sort of help facilitate that chemistry. So just to kind of highlight here, even though this is a beautiful mechanism and there's so many things that are right about it, this is not what happens here. Remembering that we've got a better electrophile in our carboxylic acid's proton there. So let's redraw this mechanism, and it becomes quite simple here when we consider the reality of what really happens with this reaction mechanism. We still have the same two starting materials. So we have our carboxylic acid and our amine. Correctly, this is still a nucleophile, and this is still an electrophile. But now we're seeing the electrophilic atom being our proton. And remember, great nucleophiles are often really good bases. So this mechanism becomes quite simple. We form a new bond between the nitrogen and the proton on the carboxylic acid. Can't have more than one bond to a hydrogen atom, so we have breaking of that sigma bond. And then we generate our products here, which are the carboxylate anion and our protonated amine. So a couple of things that I also want to make sure to highlight with this mechanism. In this case, we do see a one-way arrow. This is really not a reversible reaction. And the reason is going in the reverse direction would need to ask this carboxylate group to be a base and this protonated amine to be an acid. And if we consider what the pKa values of these, remember the pKa's of protonated amines are 9 to 10. The pKa's of carboxylic acids are 3 to 5. So in this case, the carboxylate is not strong enough of a base to take a proton away from the protonated amine. So this reaction proceeds exclusively to the right and generates the two products that we see. Just a couple of kind of comments to think about. Again, this is not the protonation state that these two species would adopt together in solution. Again, we're making the assumption here to start here that these are two separate solutions that are mixed to react. So kind of flipping back to the other slide here for a second and kind of highlighting if these two were in solution, kind of highlighting what the pKa values are, this is what would happen. Again, we would have a pH that would dictate that the carboxylic acid would be deprotonated and the amine would be protonated. Again, we've highlighted in our correct mechanism that good nucleophiles are also good bases, and protons are also very good electrophiles. So again, this problem is sort of a classic organic chemistry trick question. Everyone wants to make that amide when we react carboxylic acids and amines, and truthfully, we will see this chemistry happen, just not in this situation. And as a little preview, the next two reaction mechanisms will show us how to effectively make amides. The first one, we're going to do it in a chemical activation fashion, and then the second one, we'll actually do it in a biologically activated system.